Hello students, welcome you all. In UV visible spectroscopy, today I will discuss the topic effect of a solvent on electronic transition. So we know that to take the UV visible spectra of any compound, first the compound is dissolved in some solvent, and then that is filled, then that solution is filled in a quartz cuvette, and we put that quartz cuvette into the UV visible spectrophotometer. Okay, then the UV visible radiation falls over it, and finally we get the spectra. So what kind of solvent that should be used to take the spectra? The solvent, it may be either a polar solvent or it may be non-polar solvent, but usually the non-polar solvent is preferred. And for example, this hexane or isooctane, or suppose if we are using the polar solvent, then it will affect the electronic transition, and we have to see how the polar solvent affect the electronic transition. Now, so one of the thing that, suppose if you are using the solvent, then solvent should not absorb the UV visible radiation in the region in which the substance absorbs. So one of the point, the solvent used should not absorb the UV visible radiation in a same region where the substance absorbs. Okay, this is one of the things. And usually the commonly used solvents are for example, we may take a water. Suppose a compound is dissolved in water, then we can take water as a solvent, but this water is the polar solvent. Or either we may take a ethanol, we may take a methanol, these are the polar solvent. Or we may take a non-polar solvent, for example hexane, we may take a isooctane. So these are the different, we may take a DMF, okay, isonitrile may be taken, DMSO can be taken. So these are the polar solvent, like non-polar solvent like hexane, isooctane. So this may be taken. Now, so suppose what will happen if you are using the polar solvent? Usually this polar solvent, it affects the change in a electronic transition, because these polar solvent somewhere interact with the substance. That's why it will affect the electronic transition also. So how it will affect the electronic transition? So polar solvent, usually it may form a hydrogen bond. Hydrogen bond can be formed with the polar solvent, and it may form a solute solvent complex. So this polar solvent can form H bonding. Okay, H bonding with some polar molecule. If we have a polar molecule, if we have a polar compound, then it will form H bonding with the polar molecule to form solute solvent complex. And due to this, the fine structure of spectrum may disappear. So what does it mean? That if some interaction is there between the polar solvent and the molecule, polar molecule, then we will not get the fine structure of the spectrum. Now suppose, for example, we may understand, suppose if we want to take a spectra, UV visible spectra of phenol, and if we are taking this UV visible spectra in some polar solvent like suppose ethanol, if you are taking it in ethanol, then ethanol can form a hydrogen bonding. So this is forming a hydrogen bonding, the C2H5 C2H5OH, it is forming the hydrogen bonding with the phenol, and due to this hydrogen bonding we say there is a solute solvent complex is formed. Solute solvent complex is formed, and due to this, once this solute solvent complex is formed, the fine structure of the spectrum may get disappear. So suppose if we are taking if we have any UV visible spectra between absorbance and lambda, then in absence of polar solvent, if we are taking in absence of polar solvent, and if we are taking the spectra in presence of polar solvent, then the spectra may look something like this. So suppose this is the spectra where we can say fine structure is present. So this is the spectra in absence of polar solvent, or we can say this is the spectra in non-polar solvent. Non-polar solvent, and you can see in non-polar solvent there is a fine structure. We have the these different peaks are there. This is the fine structure. So we are getting the fine structure. Whereas if same spectra is taken in if it is taken in a polar solvent, in that case the fine structure may get disappear. So as you can see, this fine structure may get disappear. So this is the spectra in polar solvent. So this is one of the effect. No fine structure. Okay, so this is the difference if you are taking the spectrum in polar solvent and non-polar solvent. Now one thing, that suppose if you are taking the spectra of alkene, if you are taking the spectra of alkene or for dienes, then in such case alkenes and dienes, they are not affected by the polar solvent. They are not affected because this kind of molecule, this is a non-polar molecule. That's why it is not affected. It is not affected by solvent polarity. Whereas if you are taking the spectra of some carbonyl compound, suppose if you have a carbonyl compound. Now let us see how the transitions in carbonyl compound is affected by the solvent polarity. Now suppose for carbonyl compound, these carbonyl compounds, the spectrum is affected by solvent polarity. Here the spectrum is affected by solvent polarity. So suppose if we have acetone, then we have a different transition. So some of the transitions which are possible over here is N2 pi star transition, means when n electrons get excited into the pi star molecular orbital, or this pi electrons that goes into the pi star molecular orbital. So these are the main two transitions which are the allowed transition in this case. So here let us see how the solvent affect these two transitions. Now suppose if we have a transition, suppose first of all let us see n to pi star transition, effect on n to pi star transition. Okay, now so this is n electrons are present in a ground state and the transition takes place into the excited state, that is pi star molecular orbital. And suppose this is the transition which is taking in a non-polar solvent. So transition in non-polar solvent. This is in non-polar solvent. Now we have to see how the transition affects in a polar solvent. Now, so this is the energy difference. Suppose this is delta E1, and now suppose the transition, suppose the spectrum is taken in a non-polar solvent. Now, so the main transition which is possible is, one of the transition is n to pi star transition, where the non-bonding electron or lone pair electron, it goes into the pi star molecular orbital, or the next one is the when pi electrons goes into the pi star molecular orbital. So these two are the main allowed transition, we know that, in the carbonyl compounds. Now let us see how the solvent affect these transitions. Now, so first of all, let us see the effect of solvent on n to pi star transition. Now, suppose if we have this is the transition in, this is n molecular orbital and this is pi star molecular orbital, and this is a transition and this is the energy difference. Suppose this is delta E1. Okay, and so this is the transition, that is, this is shown in non-polar solvent. Now suppose if we want to see in polar solvent, what will happen in a polar solvent? So in polar solvent, this ground energy of this ground state, that will decrease. As you can see, the energy of ground state decreases like this. This is the energy of ground state, suppose. And energy of this excited state, that is pi star, energy of excited state, that is pi star, it will also decrease, but the decrease here is very less. Here the decrease is very less. As you can see, I have shown the decrease of the ground state is more in comparison to the excited state. So what will happen here? The energy difference that will increase. So in this case, the delta E2, this is greater than delta E1. Delta E2 is greater than delta E1, where in polar solvent. In polar solvent, delta E2 is greater than delta E1, or we can say the lambda 2 is less than lambda 1. And means in polar solvent, the wavelength decreases, or there is a hypsochromic shift. So that is, there is hypsochromic shift in polar solvent. So what is the reason that there is a hypsochromic shift in polar solvent? So reason is that the non-bonding electron the non-bonding electron, it forms a strong hydrogen bonding. Suppose we have this acetone. So acetone form a strong hydrogen bonding. The non-bonding electrons of this acetone, it forms a strong hydrogen bonding with some polar solvent. So for example, if polar solvent is our ethanol, so it is forming a strong hydrogen bonding. So strong hydrogen bonding means a stable molecule or stable one of the stable complexes get formed, and due to this stability, the energy difference, the energy of this ground state decreases. Whereas in excited state, no such strong H bonding will take place. So in this case, the ground state, the decrease in energy, what we can write, a decrease in energy of ground state is more than the decrease in energy of excited state. So what is the reason? Reason is that the n electron form a strong hydrogen bonding than the pi star electron. So reason, n electrons form strong H bonding than pi star, then when electron is present in pi star electron. So this is the reason. Now let us see what is the effect of solvent on pi to pi star transition. Now second one, effect of solvent on pi to pi star transition. Now suppose this is pi molecular orbital, this is pi star molecular orbital, and this is the energy difference when the transition is taking place in non-polar solvent. Non-polar solvent. Now what will happen if we take the spectrum in a polar solvent? Then in polar solvent, here the energy decrease of this ground state is less than the energy decrease of the excited state. So excited state decreases its energy much more than the ground state. So this is here the pi and this is pi star, and here overall if you will see the energy difference. So in polar solvent, the energy difference between this ground state and excited state is less than that of the non-polar solvent. So here this delta E2 is less than delta E1. Therefore, lambda 2 means that would be more than lambda 1, or in polar solvent there is a bathochromic shift. That is bathochromic shift take place in polar solvent. So what we have observed that in polar solvent, energy decrease of ground state is less than the energy decrease of the excited state. So in polar solvent, decrease of energy in ground state, is less than the decrease of energy in excited state. Now, what may be the reason why the excited state energy decreases more? Why? Because this excited state is more polar than the ground state. So when the electron is present, when the electron go into the anti-bonding molecular orbital, then what will happen? When electron is present in an anti-bonding molecular orbital, then the bond length that will increase. So we have two things: when the electron is present in a bonding molecular orbital, and when in bonding molecular orbital two electrons are present. And in anti-bonding molecular orbital only one electron is present. So that's why the bond length of this anti-bonding molecular orbital is more than the bond length of this bonding molecular orbital. So if bond length is more, then polarity is more. As the bond length increases, the polarity will increase, because we know that this dipole moment, this is equal to our that is dipole moment, this is equal to so we know that this dipole moment, this is equal to charge multiplied by distance. So, or this dipole moment is directly proportional to the polarity. So polarity, we can say this is directly proportional to charge multiplied by distance. And as the distance increases, so here when the electron are present in a pi star molecular orbital, then the bond length is more. So if bond length is more, then polarity is more. So in pi star molecular, when electron is present in pi star molecular orbital, then polarity is more. That's why interaction would be more. And if interaction is more, then decrease of energy, that will be more. So this is